models, right? We first framed how we can think of graphical models in terms of Markov graphs that give us conditional independence relationships. Then we talked about connection between Markov graphs and tensor networks, right? So one is the dual of the other, and we thought about belief propagation, how you can do inference in graphical models, which is either marginalization or max marginalization. You can do that efficiently by decomposing it along the graph, right? So it's called message passing for the same reason that you only pass messages along the graph. For a tree, this is exact. For general graphs, this is approximate. And there's a long line of work in trying to establish guarantees for this heuristic in general graphs. And in many cases, they do give good convergence guarantees. But generally in experiments, it works even beyond the cases where there are theoretical guarantees, right? So that was on the inference aspect, and then we started looking into learning, right? And we started with the tree graphical models. We asked, what is the maximum likelihood tree distribution for any given set of IID data? Right, so what we had was we wanted to maximize, so we'll just recall because we will be building on this. We wanted to maximize the likelihood of the data distribution such that it factorizes on the tree, right? So you had some of these. I guess we used Q in the previous class, and then Q was a tree distribution. And we said this is equivalent to minimizing the Kullback-Leibler distance between the empirical distribution and this class of distributions, right? And the important takeaway here is this information projection notion. Let's say this is the set of tree distributions you have. Your empirical distribution, most likely will not be a tree by itself, right? This is arbitrary empirical distribution. Even if the distribution is a tree, the empirical one will not be a tree because, it's going to be approximate, right? It's not going to match the population level distribution. And that's why it's important to project onto this class of tree distributions. And this is known as information projection because we're going to use the Kullback-Leibler divergence as a measure of information. Right? So we'll find the closest point in this set. And I commented that you cannot directly use manifold theory because Kullback-Leibler distance is not a metric, right? It's not symmetric. So if you have Kullback-Leibler distance between, say, two distribution P and Q, that is not the same as the Kullback-Leibler between the other way, right? And when P is close to Q, this is okay, they're nearly the same, right? In that case, they're nearly the same, but not otherwise. Because of course, when they're exactly equal, right, the two distances are zero, right? Both the Kullback-Leibler divergences are zero. And hence, yes, many times that's why we are making the approximation of just making small moves from a current distribution, right? So if you assume like you want to move from one distribution P to another distribution Q, but only locally, then you can kind of pretend it's a metric. And that's where people use the Fisher divergence, right, as essentially a Taylor series expansion of this Kullback-Leibler divergence. If you recall your maximum likelihood lecture, you had this Taylor series expansion, right? If you recall, there was this core function, there was the Fisher information matrix. So there's also that connection. When this is small, you can pretend it's a metric. And I haven't covered natural gradients in the class. The natural gradients makes that approximation, right? So it locally, pretends we are moving according to the Kullback-Leibler divergence, and locally I can treat it as a metric, and hence I can change from Euclidean space to the Riemannian manifold given by the Fisher information matrix. This is a side note, we are not covering it in detail, but if you come across natural gradient and its use in different learning scenarios, that's what it is doing, right? It's doing local approximation of the Kullback-Leibler divergence. Okay, so that was a connection to maximum likelihood, right? So we kind of briefly talked about it, although in an information theory class you can go much more in depth into these different kinds of distances. Because, I mean, a natural reason to use Kullback-Leibler is this connection to maximum likelihood, right? But people have all these other generalizations of Kullback-Leibler, right? So there's the Jensen-Shannon divergence and all the family of divergences. So again, you can ask why is one better than the other, right? It depends on the scenario. So I won't go into details, but indeed there is a lot of work in looking at different kind of divergences between distributions. Kullback-Leibler is the most common one, especially given its connection to maximum likelihood estimation. Right, do you see the connection between all of this? Because classically, right, estimation theory dealt mostly with maximum likelihood, right? And that meant we needed to do analysis in terms of Kullback-Leibler divergences. And if I wanted to make local approximations of my Kullback-Leibler, right, those Taylor series expansions you can think in terms of Fisher information matrix, and that leads to natural gradient algorithms. So that's why there is one way around this asymmetry, right? You can still pretend it's a metric if you're only making local moves. So that's an aside, but just wanted to kind of quickly have that comment. So coming back here, we said, I mean, this is true universally, right? There is nothing special about the tree distribution. But when we looked at the structure of the tree distribution, we could then come up with a very nice form, because we said that if it's tree distribution, the joint is factorized in terms of marginals and pairs along the edges. Right, we use this form, and when we substituted it here and just expanded, right, and argued about maximization, what would be the tree that maximizes the likelihood, we came up with the answer that it's the one that maximizes the empirical mutual information, right, along its edges. Which was very nice, right? Because now all I needed to do was compute for every pair of random variables, what does my empirical statistics say in terms of mutual information? And I just find a spanning tree on what is the one that maximizes. I can also easily extend this to forests, because if this empirical mutual information is too small, I don't even include the edge, right? I can just delete that edge. So this way I can learn acyclic graphs efficiently using spanning tree approach. Right, I mean, for general models, this is intractable, right? Because you cannot look at globally what is the best graph that fits this data, because that would involve evaluating the distribution, and if you recall, the partition function is hard, right? And even if you could evaluate the distribution, you'd have to search over all possible graphs in that family, and that's usually not decomposable. But in this case, both of that we could find a way around, right? Because if it's acyclic, I don't have to worry about partition function. I can evaluate my likelihood at each point, and search over all possible trees. I can find this efficiently, right? Because it's a spanning tree problem, I can decompose, right? I don't have to brute force search over all possible trees, which is indeed exponential, right? So I'm not going to run into that issue. So we talked about this, and in this class, what I want to do now is expand this class of distributions, right? Because I think for so many settings, it would be unnatural to make it a tree distribution, right? So the idea is, let's say there is a bunch of random variables and I want to impose a tree constraint that may be too stringent, right? This resulting model may be very wrong from the true underlying model. In other words, the model approximation error may be so high that this is not a useful model. So if you recall, there is that tension, right? Like I want my model to be, really kind of be a good approximation to the data, right? And at the same time, I want to be able to learn it efficiently, right? So I want to have both. And in many cases, this is just too stringent. Right. So one of the examples, we had a paper a few years ago where we wanted to look at just multilabel classification in computer vision. And in this case, think of it as, you have an image, you have many objects in the image, right? So let's say it's an outdoor scene, there is a road, there is like a car, that's my car, right? There's pedestrian. So there are all these different objects and you want to recognize all of them, right? In standard ImageNet training, it's just you recognize just one object in an image, right? So that's single label. In multi-label, you want to simultaneously recognize many objects in the image or many categories in the image. And to do that, you want to look at what is the dependence also between these different categories, right? So the idea is if there is a road, it's very likely there's also a car in it, right? So there is strong correlation between having a car and having road. One simple way to think about this, you can think of a factorization approach. You can think that, say, there is road, then I have a car, right? And let's say, initially there is like kind of two branches, either there is road or there is, right, like it is table, right? If there's a table, it's not likely to be a car. So conditioned on road may be table and car is conditionally independent, right? So you can come up with an approximate tree model like this where the tree represents what is the category of different objects, right? So it's kind of giving you groupings. So you can do this as a first approximation, but soon you run into problems, right? So what do you think is the main problem with this kind of approximation? If I try to put all my categories into a tree, when will this be a bad approximation in this example?
I don't know, you have like a toy car on a table.
Yes, so you certainly have out-of-domain objects, right? And we'll assume these are natural scenes. So let's kind of, and in fact, that's a good application of it, and we had it, about now it's a decade ago. We had an application like that where you can detect unnatural images, because this was back when I was at MIT. If you know the Stata building, there's a cop car on the ceiling of the building, and so those kind of instances you can recognize something is off here, right? It's anomalous. So that let's assume it's natural images. So what's the shortcoming in that case? When is the tree a bad assumption? The tree on the set of categories.
should be multiple like parents of R.
Right. So, what would be an example of that?
I mean, it depends on what the total set of object classes you have.
Right, but just think natural scene, right? Like I'm not cooking up arbitrary images.
Maybe a tree is like a hierarchy structure.
Mm-hmm.
It has a root.
Mm-hmm.
I don't know, like this, does this root corresponding to?
Right, so root, that's a good point, right? So it's not just the root, there may be many nodes that you cannot directly label or it's not labeled in the data set, right? So that's the key problem here, even if you assume hierarchy is okay, right? Like it's, because the idea is maybe like here, right? And that's why I also didn't label here, right? Because now there's first like this is like outdoor, right? And then this is indoor. I mean, root, of course, I can say all images, right? All the images are, kind of, it's root. But the problem is, I may have all these meta labels, right? So once it's indoor, right, I don't go directly to table. I first say, is it like kind of house, hotel? There could be all kinds of subcategories and then subcategories. Right, but the problem is, you're not going to label everything in the image, right? If you give the annotator, maybe they just look, okay, there is chair, there is table, right? They're not probably going to label it's a classroom. So that higher contextual information is lost, right? I mean, it's not supervised. You directly don't have in the labels. So you have to learn that in an unsupervised way. And so that means some variables are hidden. Right? Everything is not observed. Even if you make the approximation that I have some hierarchical classification of all images, let's say all natural images, I can kind of classify that, there's first indoor, outdoor, within outdoor, there's like city, there is, I can kind of come up with all these categories, right? But annotators don't tend to label that, right? They're not instructed to label those kind of meta labels in the images. And that would be a downside because if I just have a few categories, right, and I try to fit that into a tree, right, that's not going to fit this well. And the reason is, if you have a tree and you marginalize out the hidden variables, in general, the resultant is not a tree. Let's say these are observed. I mean, the leaf has to be observed, right? If the leaf is hidden, I can never identify it because, it's a leaf. So the leaf has to be observed. Let's say these are hidden. If I marginalize out all of this, what would be the resulting graph?
If you marginalize the hidden nodes, when you just get a tree of like depth 1, it's like everything connected to the root.
Let's make it simpler, right? So let's just marginalize in the simpler example. I marginalize out this hidden node. What happens? I can even write this down, right? Let's say this is x1, x2, x3, right? There's also conditional independence, right? So let's say this is h. This probability of h, and then over h. Let's say even h is binary, it's just two terms, right? But what happens? Exactly, right? So all the structure is completely lost. So in general, this would be just a complete graph, right? So I can impose all this nice structure, but if some variables are hidden, right, I cannot just glean the structure by looking at the observed graph. If I just look at the graph between observed variables, right, I don't see that structure. And in so many scenarios, we cannot expect the entire tree to be observed, right? And that's why this is a bad assumption, right? So this was the Chow-Liu algorithm where you assume every node in the graph is observed. And it's very rare to have that be a good assumption in practical applications. Is that clear? And that's why, you know, there's a whole kind of series of works looking at estimating graphical models just on observed variables, right? I told you there's like more sophisticated analysis. And that's great to advance the theory and foundations, but in general, those algorithms don't tend to give interpretable results on real data sets. And I would argue this is the primary reason. In general, you would have, inevitably you have hidden variables, right? And you try to just fit a sparse graph or some low complexity graph on just observed variables. You know, not much is going to come out of it, because in general, that'll be a complete graph. Okay, so on the other hand, if we try to explicitly estimate a tree with hidden variables, right, this is arguably much more effective in learning about the underlying distribution. And so that's why we'll address now this next question on how to estimate this well. Any questions here? Right, I mean, just to kind of complete thought on this application, we did have a paper where we looked at the conditional distribution of the categories or the labels, condition on the input image, right? We said this is a latent tree model. So that's the short form for latent tree model. And we, you know, I'll show you the methods to estimate the latent tree model. And when we did this, we could find right, that in an unsupervised way, we could learn like kind of these meta labels or categories, right, that were not given by the annotators. For instance, the algorithm automatically picked out that there's a whole group of bedroom scenes, right, whereas there was no label bedroom. Same like kind of, you know, there was like grasslands and forests, everything it kind of automatically picked up. And so the idea is that would combine supervised and unsupervised learning, right? Because there's the part here, because of this latent variable, that would be unsupervised. And of course, this part is supervised. So I'm combining two of them. But this is not the standard form of semi-supervised learning, right? In the standard definition of semi-supervised learning, you know, I have this set of variables, some of them are labeled, some of them are unlabeled, right? But in this kind of problem, none of these latent variables are ever labeled in any image. So this is much harder, right? So you have supervision for some set of variables, which is the y, but there's a whole set that is hidden throughout the data set. So that's why I would still call it unsupervised, because you have no supervision for those hidden labels. And this was much more effective than standard methods, right? So what does the standard method do for multi-label? You can just train separate classifiers in the end, right? You have a deep network, in the end you just train separate classifiers. Instead what we did was, you know, we had the neural network, in the end it was a latent tree model at the last layer, rather than independent classifiers. So the idea is there's some deep neural network, right, that transforms the input image. If it was the standard approach, this would be just independent classifiers. On the other hand, the latent tree model looks at now, right, it introduces like latent variables, right, sorry, it's a tree. and then outputs the different categories. So between here, this layer, right, this conditional distribution, you can frame it as a latent tree model. Or more generally, right, because it's features at some layer, it's some transformation of that input. That's a latent tree model. Because I don't want to be doing directly on the pixel space, right? That's bad. But I can use the deep network to give me features, and then I can try to factorize it as a latent tree model. And this was shown to be especially effective for categories which tend to be very noisy for independent classification, right? For instance, the baseball bat and the ball, right? That's too small. It's only some few pixels, then you cannot kind of recognize it very easily. Same the hockey and the puck, all these, the contextual information should help a lot. And in a way, the deep network is implicitly anyway going for context. This makes it more explicit because it says, look at the likelihood of whether there is a baseball bat in the picture, right? And based on that, I'm going to also decide whether there is ball or not, right? I'm kind of using this joint distribution and making my decisions of what objects are present in a joint way. So that's why it can be more powerful compared to independent classification in a multi-label setting. Does that make sense? Any questions here? Yeah? So there are many other applications. If you look up many of the works that have developed latent tree models, they are in phylogenetics. So philo means, of course, I guess it means old, right? Maybe not. So phylogenetics is about the learning about the evolutionary tree, right? So you have now, right, all these species that are currently alive today, but then we have all the extinct species, right? So you can map it as far back as you want since the beginning of life. And so you want to now have the hierarchy of which species evolved to which current day species, right? So that's called the evolutionary tree. And again, there the question is, just given now the genome of alive species, can I recreate what did the genome of extinct species look like, right? Can I come up with, again, which species are siblings, which ones are closely related, but as well as estimate what was the likely kind of genome for all the extinct species, right? And that's two parts to the problem, right? You want to learn the model, you also want to infer about the hidden variables. And if you recall, when we talked about spectral methods, we also discussed there's these two parts, right? Because one is just like learning the tree, like learning tree and parameters, right? And then the other is inference of hidden variables. So for each given sample, once I know the model, I can infer what is the most likely hidden states. Right, but the first step is learning. So that community has looked extensively on learning these latent tree models because they want to map out the evolutionary tree.
Can I ask, so the hidden nodes, how do you decide like how many there's going to be? Is that something that you constrain?
Yeah, so now when we address the how to learn the tree, that would come up. Right, so yes, in practice you can also ask how to, I won't give this as fixed, let me also learn this from data. Right, and that's also an important aspect because if you put too many hidden variables, right, then that's like an over-parameterized model, right? That's not kind of capturing the true underlying distribution and may give you wrong results, especially if you want to reason about what happened in the past, right? So not just fit the observed distribution, I really want to interpret the tree. It's important to get the right structure, because you can always add more hidden variables and make this a binary tree, right? Even this one, I can just add now hidden variables that are degenerate. I can push everything to becoming a binary tree, right? But in practice, I don't want a binary tree, right? I mean, that has the largest possible number of hidden variables and also the largest depth. For so many reasons, I may not want that. Of course, there may be some settings where there may be just one hidden variable, right? That's this factor model. If you recall, we did this factor model, right, when we did the tensor methods. Here, I don't want a lot. I mean, you could have many, many nodes here, right? But there's just one hidden variable, so that's a factor model. Right? In that case, it's just there's one hidden variable that factorizes everything. So we do want to be informed again by data on how many hidden variables we add in general. But we'll come to that. Good point. Any other questions? Actually, when it comes to the phylogenetics community, they didn't worry about this, right? Because all they wanted was just a binary tree, right? They just wanted which species are close to one another and which ones are not. And of course, there it's usually bifurcation, right? It's you don't have suddenly many species that arise out of one, right? So it's usually evolution happens because one species mutates to another and then another. So they mostly consider binary trees, and that's a reasonable assumption. Although there is sometimes, in the newer models, the binary tree may not, or a tree model, even in phylogenetics, may not always be a perfect assumption, because the one that violates this is what's known as viral transfer. So sometimes viruses can kind of transmit mutations across different species, and so there have been some works that try to extend beyond just tree models, which is interesting to me. There is, how the evolution process, you always think of it as a tree, but there could be some deviations to that. Anyway, that's an aside. Good, so if there are no further questions, we can now get into learning, right? First the tree structure, then we can talk about learning the parameters. So actually learning parameters is easier. Maybe we can quickly do that and then learn the structure. How about that? So let's say I give you the tree structure, right? So I give you something like this, right? So if I give you this tree, can I actually learn that? Can I identify that? Can I uniquely identify the tree I have written down just based on observed data? What do you think?
There's the original invariance.
Right, and where is the redundancy or?
Around the roots.
This one, right? Because it's only degree 2. I can just marginalize this out. Right? Nothing changed. And so that's why we will learn what's known as, right, the minimum tree in the equivalence class. And that's true for any hidden variable problem, right? There's an infinite set of hidden variable models that would fit the data. But what I want is the one with minimum complexity, right? So that's the Occam's razor. I want the simplest explanation to my data. And hence what we will aim to do is to compute this minimum tree. So the minimum tree means all hidden variables have degree, at least 3 or higher. And no no leaf node hence can be a hidden variable. And you cannot have a degree 2 hidden variable. Is that clear? And also you cannot have two variables to be perfectly correlated with one another, right? So that would be degenerate. Because I can always just split this one variable into two variables, right? The same variable. I mean, that's not meaningful. Hence, I should assume that there's some independent randomness in each variable. So that means the conditional distribution of one variable given another is not one, right? So it cannot be just deterministic. And hence, I mean, that's a very simple assumption to make. So that's what we would call non-degenerate distributions, right? Trees that satisfy the condition both in terms of structure and parameters. And so we'll aim to learn that. Okay, so that's with respect to the equivalence class. So if you want to estimate parameters, how would we go about doing this? Let's say, for example, I give you this tree as the structure. I already tell you this is the tree structure. How would I estimate the parameters of the model? If you want to think back to the previous classes, what's the connection? How do you estimate the parameters of this factor model? How do you estimate parameters here? Right, so in the spectral methods class, that's when we looked at, right? If you recall the CP decomposition, you're looking at the joint distribution of these variables, right? And through tensor decomposition, you can estimate this model, right? And as I said, let's assume discrete or Gaussian, you can also extend it beyond, right? You can kind of put general features here, but we will simplify to make it discrete or Gaussian for the sake of argument. And in both cases, we can estimate, right, the parameters of the model. And so this is true for just one hidden variable, right? So what if I had, of course, we also looked at the other model, right, with hidden variables, that's a tree. What was this one? What was this model called? Hidden Markov model, right? We could also estimate the parameters here. We already, again, knew the structure, right? So, because I gave you what was the sequence in which the data was collected, and so I already knew the graph here. So we were estimating parameters in this example as well. And so from these to go to a general tree is actually not that difficult, right? Because what I need is, if I just looked at the moments, right, of every group of siblings, it's a factor model, right? So I can just now estimate these conditional distributions just here, right? So I can just take this group and this group separately, do tensor decomposition, and learn these conditional distributions of each of the edges here. Do you agree? So now I guess the only thing left is this edge, right? How do I learn this distribution along that edge? Just intuitively, how do you think? What should we be doing? First of all, do you agree with the first claim, right? I take this group of variables here, I do tensor decomposition, I can learn about what is the conditional distribution of each of this, right? Because that's exactly what this decomposition will give me. And similarly, I can do it for all these edges here. The only edge that's left out is between the hidden variables. So how would I estimate that?
Can I just do another SVD get this decomposition
SVD on what?
on the two hidden tensor?
Well, you don't have the hidden variable data, right? That's the whole challenge. If you did, yes, right? Then you can just even, I mean, if you directly observe these two variables, right, you can just find the joint through empirical distribution. SVD would do dimensionality reduction, but that's that's only to kind of fit it to some fixed dimension. But we don't have hidden variables, right? That's why this is hard.
Are you doing like MLE?
No, this is not MLE, right? So MLE is hard. That's why I didn't talk about MLE here. Because if I try to frame this problem, this is NP hard, right? So I cannot do this. Instead, what I'm trying to do is some consistent method, right? Which means if I had infinite number of samples, it should give me the correct minimal tree and the correct minimal model. Sorry, the tree is already given in this argument. We want to learn the true underlying model, assuming it's actually coming from a latent tree distribution. So that's the notion of consistency, right? So asymptotically, I should get the right answer. So that's a much weaker setup than what we had with the fully observed tree, but this is a hard problem. Yeah, so we won't be asking for MLE. All I'm asking is, suppose you have infinite amount of data. How can you ensure you correctly find this distribution between the hidden variables? Let me call this H1 and H2. The only thing that's kind of left to be estimated is this joint probability. Right, because if you want to again, let me write down the factorization form. I think that'll help you, because this joint distribution on the observables, right? Now I'm marginalizing over these two variables, right? And so that's this joint distribution, and then there is the product of the conditionals. So let's say this is x1 through x6 here. Right, so I'm just like writing out the factorized form. Right, that's my joint distribution. Do you see that? I just factorized along the tree. Right, so these I've already learned, right? I told you if I just do tensor decomposition in this group, I can get this too. And I can also get the marginal of H1 and H2, right? Because when I'm doing tensor decomposition here, what I get is both the conditional and the marginal. So I also know probability of H1 and probability of H2 separately, right? These I know. But what I don't know is the joint between them. Because so far I have not used any joint information at all, right? I've only looked at the observed distribution in this group and in this group separately. So there's no way to kind of know what is the correlation across the groups. How do you think we can do this estimation? Do we have enough info? What do you think? Information?
Can you use like the base rule to try to get some expression for like the joint distribution?
I mean, we already have the joint distribution here. I mean, over the observed.
For H1, H2.
Okay, that'll be in terms of conditional and marginal, right? But how do I get the conditional? Yeah. Recall, all I have is just the observed data, right? But what is the, if I look at, So I already gave you a hint, right? So far we've only looked at distribution only on those groups, right? We haven't looked at any relationship across groups. So how can you use that hint? You see, if I only looked at this set of relationships, there is no way to estimate that age, right? Because I have not had any outgoing information. So how would I estimate something in between these two groups?
I guess we just put them together and use what they have already together, like pairwise distribution of each one and each two.
Sorry, what you'll put together? Can you repeat?
So we look at all the observed variable and we use what we have learned for each group.
Yeah.
Then we get the inference of H1 and H2 pairwise distribution. And we use this to calculate the pairwise.
Right. So in a way, you're creating fake data, right, by doing inference. Because if you recall, I said, right, you also have the marginal of H1 and H2, right? So I can now find like the posterior of each of them, right? H1 given, say, x1 through x3. And similarly, I can look at H2 given x4 through x6. Because I've estimated these. Right, both these models I know. Right here, it's the base rule. Right, I can apply base rule here. So I can compute these two. So if I can compute these two, I can essentially, there are different ways, but in the simplest one, you can just draw samples from this posterior. Right, you can ask what is the most likely hidden variable. Right, for each observed sample, what is the most likely hidden variable? And so that you can treat it now as your real data, right? So you can just look at the joint distribution of the empirical between what you inferred. So essentially, let's just say H1 star is this max, right, over H1. Similarly, H2 star. And then I can find like the empirical distribution between H1 and H2 to be based on this inferred hidden variables. Does that make sense? I mean, these variables are hidden, right? But once I have my partial model, I can come up with what is the most likely hidden state, right? What is the most likely value this hidden variable took? And once I have this, I can look at the empirical statistics on those inferred variables. I know this is not the same as looking at actual values from the draw, right? Because this could be wrong. But it turns out asymptotically that's okay. You can get the consistent estimate. Right, it's roundabout because you don't have hidden variables, you first infer hidden variables, then you compute statistics among the hidden variables, and you can proceed to get the full distribution. There's an alternate approach. So this is one approach. There's an alternate. What else can I exploit given that this factorizes along the tree? Can I exploit it in a nice way?
I was just wondering, can you use like MCMC methods here?
So MCMC is to kind of get to some desired distribution, right? If I want to sample from a complicated distribution, I can eventually converge to that. I mean, essentially you can use MCMC for any hidden variable model, but in general that tends to be expensive. So we want to go for simpler methods because of all the tree structure. Can we do something better? So that would be the reason, right? So roughly, like what else you can do here is, you can go through a path in the graph, right? For instance, I can go through this path. And it's, if I want to look at the joint distribution between these two nodes, I can write it in terms of like going through, right, this product along this path. And hence I have like a decomposition form. Right, so the idea is if I just look at this joint distribution, there is this factorization, right? So another way to kind of say this is I can come up with a quantity where it factorizes along the tree, right? I mean, we know the distribution factorizes. And hence I can think of like finding weights along the edges. And some weights are hidden because they are between hidden variables, right? And even if it's between observed and hidden, I can still not compute it because I don't have the hidden variable. But I can compute my distances between observed variables. So essentially my probabilities, I can convert them into distances and really argue in terms of distances. So, you can do that both for discrete and continuous. For discrete random variables, this distance between any two nodes. So, you have an arbitrary tree. I can look at distance between any pair of nodes, right? Not just neighbors. So this is now nothing but log of, I forget the exact form, we can check in the notes. I don't have it here, it's in the paper. It has something to do with the joint, and I think maybe it's the square root of the marginals. We can check the exact form. And the claim is this distance is additive along the tree. Maybe the square root makes it okay, right? Because you have the product. So we'll check the exact form, and if it's Gaussian, this is nothing but the correlation coefficient between the two nodes. This is Gaussian, this is discrete. But the claim is that these trees possess an additive metric. Meaning these particular distances should add up on the tree, right? So meaning if I look at distance between any two nodes, I and j, that's nothing but equal to distance along the path of nodes, right? So let me call this k and l, and k and l is along the path. And you can see the factorization property along the tree should give you this. For Gaussian, it's more direct to see, because if you think about Gaussian distribution along a Markov chain, right, in this simple example, it's nothing but product along the path of the tree, of the chain in that simple example. But this is a claim, right? So for whenever it's a tree graphical model, you can always find this distance. And so essentially you're converting the product of probabilities to now log, and you're converting them into distances. And these distances are positive. And they're zero only when the two nodes are exactly the same. Right, so that means it's degenerate, right? You cannot have two nodes be exactly the same. And that's why we call it a notion of distance, right? If these two variables have a large distance, that means they have a weaker correlation. They are very close to one another, they have a stronger correlation. Okay, so we use the factorization on the tree to convert them to distances. And hence we can now talk about matching distances, right? Because now I can ask, so what I have right now, the problem statement is the only observed distances are between the observed variables, right? Observed variables. But what I want to estimate, right, I want to estimate both the tree, if I want to do the structure estimation, and all the distances along the tree, right? So that is both hidden and observed. So that's how I can frame my both structure and parameter estimation problem through this. But we'll primarily look at structure problem because that's the one where, right, the use of distances can help me infer the structure. And once I have that, I can infer hidden variables and estimate the parameters. Is that clear? And based on observed data, I can estimate what these distances are, right? If I have now samples, I can estimate what my correlation coefficient is. So I can come up with empirical estimates of these distances, and I want to fit them all into a tree. But I don't have the distance between every pair of nodes in the tree. I only have them between the observed variables. Right, so this now becomes purely a combinatorial problem, right? Because it's one about matching distances to a tree. So think of it as now I have this end-to-end distance along the tree, right? So I can tell you what is the distance between the first node and fourth node, right? Third node and fourth node. So I have all these end-to-end distances. But there are many variables that are hidden. I don't know what the intermediate distances look like. Right, I have the distance on the entire path, but I don't know the components. And given your experience with trees, you can see that this can be solved efficiently. Right, I mean, you would imagine, because there's a nice decomposition part of right, breaking down each path into its components, and many paths share the same edges, right? So that's why you can look at, right, what are the common parts and try to estimate that. So that's how we change our tree estimation problem. This is certainly not maximum likelihood, but we hope we can get a consistent answer, right? Meaning, you had exact value of these distances, meaning you had infinite data and you had the correct values. Can you correctly find the underlying tree? So how do we think we can go forward? What would be the first step towards solving this? Where would I start? Just take a guess. I'm given end-to-end distances, I want to find the components. What would be a way to break down this problem into simpler tests or simpler modules?
Find the edges within like a neighborhood, like a cursor.
How do you know the neighborhood? Here I'm not knowing the structure anymore, right? My goal is to find the structure. right? Find the tree. Yeah.
Expressed as a system of equations. So since it's a tree,
Mm-hmm.
there's only going to be one path. So you just write a system of equations, one for each possible pair,
Mm-hmm.
where one side is just the end, like the complete path distance, and it's a sum of the hidden edges, and then you just solve the system of equations.
Right, but the challenge is this is a big global system, right? And we don't know. Can you break it down into simpler parts? Usually with trees you can, and that's why I want you to think, can you, instead of solving it globally, can I make it simpler? And also it's more intuitive and interpretable.
Can you use like a greedy approach where you try to find the closest
Mm-hmm.
distance?
Okay.
To the closest distance between 2 points?
Two observed points.
2 observed points.
So that I already know, right? Because I have all the distances between observed points. So what does that tell me? So let's say x1 is closest to x2, right? Let's say that for the sake of argument. How does that help me?
Because it gives you a good idea that they're share
Mm-hmm.
a fewer number of edges to get to the 2 points.
So would the closest to a node always be a neighbor? Sibling? It's not, we call this siblings, right? So two nodes that share a hidden variable. Remember, the distances are positive. You take any observed node, right? And ask what is the closest observed node to this. Would that be a sibling? What do you think?
Isn't there like a graph optimization problem where you have some points in space and you have to select the optimal points that creates like a tree or minimum distances?
Steiner tree?
Yeah.
So again, right, there are approximation methods, and there are kind of, I guess the difference is you're not matching end-to-end distances. You want to just minimize the distance on the tree. This is different.
Okay.
Here the input is different. We are matching, right? I've already told you these should be the distances between the observed nodes. So James kind of started there, right? So we want to look at relationships between close by observed nodes. So I asked the question, how can I tell which nodes are siblings or not? How do you think I can test for sibling property? So that's a sibling test, right? So I want to just ask if two nodes share the same hidden variable. How do you think I can test that? So let's say there are these now two observed nodes, and the claim is maybe there's all the rest of the graph, right? I don't care about any of the rest. I just want to come up with a test that tells me, do they have the same parent or not? Okay, I'll make it even simpler, right? Before we get to the sibling test, let's just do a parent test. So in this case, let's say, both are observed nodes. So if I is a parent of J, right, meaning J is a leaf node, I is its parent, and the rest of the graph is only connected through I, right? When will this be true? How can I test whether this is true or not?
So distances from J to all the other nodes is
Exactly, right?
the distances from I to all the other nodes.
it's going through this, right? So exactly. So it's like d from, say, j to any other node k is this distance plus this, right? And if k is observed, I can, right, I have all these values. So I can do a simple equality test. Right? So can I extend it to siblings? What part of it is shared between two siblings, if you think about paths? Right? I mean, obviously I need a witness here. K was some other witness here, right? And I want to look at different k here and check for if they all match. So similarly, I can look at different witnesses k here. What part of the path is common if they're siblings? Like all this, right? So if I look at, so okay, but I don't know that, right? Because so now, even though I know I and k because they're observed, if this is the case, I don't know what this hidden variable is. So how can I solve this? Because I don't know the hidden variable, right? I don't know these two distances.
Test the differences. Test the difference.
Okay, and what should that be equal to if they're siblings?
Just should be a constant.
For k, right? Is equal for all k. It doesn't matter what k you choose. So it's a simple test, right? I can quickly tell whether they're siblings or not. Right, so as you can see, it's some very simple tests to build a tree recursively, because I can start with this parent test and sibling test. You know, I can decide which ones are siblings. You know, I can get now the inference of my hidden variable, right? Like I can do tensor decomposition, I can find that local factor model, and I can keep building the tree higher and higher up with this. So, you know, it seems like a scary big problem in the beginning, but they're very simple local tests to infer the tree. Does this make sense? So essentially you can recursively group, you know, you can start with one candidate set of siblings, right? Then you have like hidden variables for that, you estimate now, right, also statistics of hidden variables, you further do the sibling test, you keep building the tree deeper and deeper each time. Does this make sense? Right, so again, the very simple divide and conquer, right? So with trees, that's the nice part. And you can use that effectively to essentially do, right, it's like triplets test, right? I'm only looking at 3 variables at a time, and I'm looking at, okay, do their statistics align or not in terms of these distances. And in practice, of course, I won't have exact distances, right, because these are computed from samples. And again, the underlying distribution may not be exactly a tree. So I can relax this to some thresholds, right? So I can, you know, tune what the threshold is, and I can try to come up with it, with a tree. But you know, in a way, it's still a bit messy because I'm locally trying to build parts of the tree. I can't easily regularize for hidden variables globally in the graph, right? So it's not like an easy control, like I think what Alex was asking earlier. That's not so easy to do. You can still tweak all these hidden hyperparameters and try to come up with a control, but it's because each test is local, you can't easily control this. And so there is a method that makes it more convenient to do, which kind of combines the, you know, some kind of global way to kind of estimate, but also has local tests, right? It's both local and global. And that's called like essentially what it does is it draws inspiration from the Chow-Liu algorithm. So it's called Chow-Liu latent tree for that reason. And the main idea is, right, so why not in the beginning try to fit the data to just a tree distribution, right, on observed variables. And then progressively I can try to add hidden variables locally in the neighborhoods. So I'm first trying to still globally get a tree and kind of locally grow the tree in different parts. So one intuition is, let's take the example we had before. This is my latent tree that I want to estimate. But what I'll do in the first step is to estimate just a tree on observables, and let's say it looks something like this. Right, so let's say this was just for argument's sake, right? So I can begin with a tree like this and then try to infer that there are hidden variables in local neighborhoods. And the intuition of starting it this way is I can like globally find like a spanning tree, right? So the intuition is I could just say, give me the minimum spanning tree with respect to all the observed distances. Makes intuitive sense, right? Because I have a bunch of distances. If I could directly fit this to a tree, fine, right? I don't need to add any hidden variables. Now I can look at where is the mismatch and try to add hidden variables only as needed. So this would give you like more global control on how many hidden variables you add. And so this is kind of like, the earlier approach we had was bottom up, right? You were only doing local tests. You were only building parts of the tree and trying to match all that together. This first starts with a global kind of tree construction. And then what it will do is locally it'll like look at neighborhoods on the tree and see if do I need to add hidden variables. So it does divide and conquer after it does the global construction. So again, is this a correct approach, right? It turns out it is, but it requires some lines of proof to show that. But I want to first make sure you understand the intuition. So it's almost like you're progressively growing the tree to add new hidden variables, right? You first just ask, why don't I just construct a tree just with observed variables? Maybe that's wrong, but let me start there and let me look at how much it violates this additive property I want, right? This, where was this? Additive property on the tree, and based on that I can locally test for those violations and add hidden variables. And it turns out that this is possible. The main key idea, which is really cool, is, right, what is the relationship between this latent tree and the minimum spanning tree on just observed variables? It turns out that it's a simple kind of contraction-like rule where the hidden variable just collapses to its closest observed variable, right? I have distances between all these nodes in the tree. What I can do is I can just go and collapse each of my hidden variable, merge it with its closest observed node. Of course, if it's many levels of depth, I can progressively collapse, right? So in the end, I remove all my hidden variables through collapsing, and we can prove that it turns out to be the minimum spanning tree just on these observed distances. So this is kind of like obtained through like collapsing of the hidden variables. And that's why you can like kind of keep some local property, right? So that kind of shows why this minimum spanning tree is a good initial point to start trying to find the overall latent tree. Does this make intuitive sense? Right, so that's a nice marginalization property of latent tree models. You know, of course, if I marginalize the distribution, like we discussed before, in general, that's a complete graph, right? But if I try to approximate it to a tree distribution using these distances, it turns out that's a very simple rule. What I'm doing is just collapsing that hidden variable into that observed variable. And that's how I get this minimum spanning tree on observed variables. Any questions here? Right, so we can start with this minimum spanning tree as the initial point. And what happens is that here all you need to do is just, so let's say that is, let me write this here. So I start, let's say, with this minimum spanning tree. Just on observed variables. This collapsing property, right, makes it kind of clear that all I need to do is do all these sibling tests and parent tests just on neighborhoods in this minimum spanning tree. So I take every interior node in my, this tree, and just do the testing only locally. Right? The other variables are irrelevant for testing, and so it becomes much less noise prone because I need to do only these tests on small groups of variables, not, you know, if I have like 1,000 variables, this is bad, right? I can't be doing these tests and trying to match distances, especially they're noisy. But if I do it on a small group, that is great. And if you indeed have a pretty distributed tree, those neighborhoods become small, right? If the degree is small, you have small neighborhoods where you need to test, and that's why it's much kind of cleaner, and you can also control how many hidden variables you add, and you can look at the overall data fitting. So this way you can learn both the structure and parameters in a latent tree model. Any questions here? Good, so I guess we are now done with graphical models. In the next class, we can look at other topics. I'll probably do some competitive optimization. I do want to cover also neural networks, representation and generalization. But see you next class.